instead of P, well, I'm going to write P in terms of what it depends on, right? Which in this case is big P, big Q, and T. And then I have Q dot, which depends on P, Q, and T. And then I have H, which depends on P, Q. Oh, wait, I forgot we were defining this in terms of order. Yeah, so this depends on P of P, Q, and T. And this depends on P, Q, and T, all on T. DT, right? Okay, so
did you want to use your G and your?
Well, I could. I'm kind of being a little loose with things because it's confusing to remember what these were for. So I'd rather just write it like this, but know that this technically is G, right?
Okay.
But yeah, it's just it's a reparameterization of P and Q, in other words. Okay, so here's the interesting part. So if you take a look at this, so my claim is that in order for Hamilton's equations to be preserved, what I would want to happen is I would want this to be P Q dot minus H of, I guess, P, Q, and T, right? Something like this, right? Now, here's the issue. We don't have this. Specifically, you'll notice that these are not really the same expression, right? Because this and this part are not the same. Similarly, it's I'll show you in a second what I mean, but this and this might not be exactly the same. And so, in order for, basically my argument was, well, if this gets minimized properly, then you end up getting Hamilton's equations of motion. If this gets minimized properly, you should also get Hamilton's equations of motions with now the new coordinates, right? If that makes sense. And so what I'm saying is, essentially, since these don't have the same form, you can't just do arbitrary coordinate changes and expect to get the same thing. So the question is, what does...
In what sense do I not see the same form there?
Well, so if you look at this is some function. Remember, this is like a function of P, Q, and T. This is a function of P, Q, and T, I guess.
Yeah.
And so these are just two functions of P, Q, and T multiplied together, but it needs to be P times Q dot, and it's not
it needs
necessarily.
to be the actual...
Yeah, and so there's the crux of the issue. So I guess I'm going to now back up and let's talk about a related question. What makes a Lagrangian unique, right? I don't know. What do you guys think?
Well, it's...
I can define uniqueness up to a certain point, but what...
there's a null
what's
space.
The equivalence class?
Yeah,
There's a null space of the Euler-Lagrange operator.
Total derivatives.
Total derivatives, what else?
Total derivatives of functions of the underived.
Yeah, it has to be,
just the Q's.
Yeah, it has to be total derivatives of functions with respect to time. And the reason that works...
But just of Q's and T's.
Functions.
So it can't be a function of Q dots.
Right. Yeah. I guess.
So yeah.
Well, I mean, but then,
it's kind
I
of
think it can, but then you have to go up to the next level in your Euler-Lagrange equations. Right?
But if you just do the first jet space Lagrangian, it changes the dynamics.
And maybe let's
but you could do that if you had like a second order Euler-Lagrange equations.
Yeah, because I mean you can extend the Euler-Lagrange equations.
Olver does the whole thing all at once.
Yeah.
And I guess let's simplify things and say ultimately it has to depend on t. And what happens is you have a total derivative over time. So what happens when you slap that in an integral, which is with respect to time?
Evaluates it at the boundary. Yeah.
Right, exactly. You end up getting basically just f of t2 minus f of t1, right? And so this doesn't vary when you do your variational calculus. And in other words, it doesn't change the answer you get for,
because you have like fixed boundary conditions. So.
Yeah, exactly, right? So since T1 and T2, they kind of, we fix these boundary conditions where they have to stay the same, then you end up just getting this fixed value added on, and basically the action, the minimum that you're looking for of action, or that stationary point of action, doesn't change at all, right? Because essentially this is just adding a constant on, right? Now, there's also, I guess, another thing you could do, I don't know. Yeah, I think you can multiply the Lagrangian by a constant as well, and I think that would give you the same answer, which is also kind of interesting. So what I mean to say by that is there's sort of, with uniqueness, some things we have to take in mind, right? I can write down two Lagrangians would seem to be different, but because one perhaps is like a total derivative added onto the first, they actually give you the same equations of motion. And I would argue that they are the same Lagrangian in that sense, right? We could define an equivalence class, which is all of those things being the same thing, right? And that's kind of the only meaningful difference we would care about in physics, is what actually gives us different, motions, right? And so I guess the question now becomes, this is kind of a Lagrangian now. We reparameterized it with a Hamiltonian thing, but the question is, what would keep this, or what would make this the same as this, right? And in order for that to happen, the one easy thing we could do, and this is called a canonical transformation, is that we say, okay, well, let's say that this is the same thing as this, but plus a total derivative with respect to time, right? That's kind of the natural assumption, because then at that point, these are basically the same Lagrangian, and I'll get the same equations of motion, but because of kind of the way it's written like this, then I'll end up also getting Hamilton's equations of motion, right? Now, I guess I should back up really quick, and we're talking about this action thing, and we want it to have a particular form. What's really interesting is, if I don't really care as much about the form of Hamilton's equations, I can do this anyway, but we kind of like it having a symplectic structure, right? Let me explain what I mean by that. So normally, we kind of have this thing where we have P being partial of H with respect to Q, P dot with respect to Q, and we have that Q dot is, that should have minus sign, right? Somebody check me on that. Yeah, I think that's right. Normally we have kind of this structure, and what this means is, another way of writing this is I was to take the Hamiltonian over here, so like, I guess I could do it like this instead. Kind of like the gradient of the Hamiltonian, almost. It is almost like, let me see what's the best way of writing this out. Maybe like this, just more explicitly. Okay, P dot and Q dot. And then over here.
P and Q.
So,
Yeah, I think you want them same order. Yeah.
yeah. Okay, so I want this to be, the P will be Q. Okay, so this needs to have that and that, but it's going to be a derivative. So, I don't know how to properly notate that. Anybody have a good idea?
So you don't just want multiplication, right?
What is
I'm trying
I
to show
I
the symplectic
see.
structure, I guess, of the space. So it should look something like a symplectic matrix times this is this.
Oh yeah,
right?
I've done that before. I can't remember. Let's see.
Well, it's gonna
P-
be. I see.
Oh, you let that. You
it's,
let an operator act on
You got-
H.
see that
It's
vector,
like-
it's just
Do you want P and Q there, or just H on the?
It's like
other
Oh,
side.
maybe it's supposed to be H.
Maybe it's
yeah.
just H.
omega.
Yeah.
Yeah.
I think you just want H there.
P of whatever we're doing. Like, so this would be like G, H. It should be this, I think. Well, not D. This should be just D. So this is.
Like
Q and
H
G.
idea.
I think you just want H there. Yeah.
Yeah, so let's see if we go H.
And this is gonna be like G.
Oh yeah. Okay.
If this is what you're saying, this is what we're saying.
Oh I know what you want. Oh.
And so here omega would be like something like 1 negative.
Oh gosh.
Yeah, okay.
I've done this
Yeah.
before. So you do- you-
I think there's a way of writing the derivatives in terms of the original.
Okay, so just do it at one. Just do it one step at a time. So just write one column vector equals another column vector. Just stick those guys in it, and then, you kind of would prefer not to have the minus sign, right? And
Yeah,
so you
I-
try
yeah,
to
let's do this
you
a
try
step
to
at a
you
time,
try to
right? So,
absorb
yeah.
that in. Oh, and you would prefer to have
Ah,
kind of a p partial.
this is-
A p partial where there's a p dot, right? And so you have to have a matrix in between. So yeah, and put the h on the outside first for that vector.
Yep. So something
Just put the
like
h on the outside,
that.
and then say that that's some matrix times the normal order and with no minus sign. So partial p on the top and a partial q on the bottom, h
Yeah,
outside,
okay.
and
That's
then
what I was
what would
looking
be
for.
the
Yeah.
matrix?
Yeah.
That's this.
Yeah, that's
Okay.
that half of things.
Yeah.
Exactly. I just want it to be a little bit less like
No, you're good.
obtuse, I guess.
So
for,
zero,
Like,
so 0 minus 1 in your first
no,
row.
I mean like that's pretty clear.
No,
Like,
no,
you
no,
have to have a
it's
little
just
bit
like,
of
yeah.
background, right?
So 0 minus 1 first row, right? There you go.
Okay, there we go.
There's your
Okay,
symplectic
so
matrix.
we have this kind of matrix structure right
Yep.
here. And basically what ends up happening is because this matrix is the way it is, we end up having this is the negative of the derivative with respect to the other thing and vice versa, right? And that's what we mean when we say it kind of has a symplectic structure on the manifold. Or that's kind of a simple version of what we could say. So I guess what happens is we could do other coordinate transformations, but it wouldn't necessarily be the case that this matrix is expressed the same way. Basically, if we did a different coordinate transform, like it kind of, you can think about like if you were to write a matrix in a different basis, you would get a different looking matrix, right? And it might not look nice like this. And so that is to say Hamilton's equations of motion as we want them to be, these simple ones might not be preserved. But you will get something that is preserved. That is to say a more complicated looking symplectic form, but it's not the simple one that we like. And that's kind of the issue with that reason.
But
So-
it should be related by like a similarity transform or
Yeah,
something.
exactly. Yep. They will be similar to each other, but
Well, I think they'll be similar up to, I mean, J kind of thing.
J?
That matrix, like
J kind of thing? What do
with
you
the J,
mean by
there's the symplectic J matrix thing there, right? And so that's
Yeah, well, I'm just saying that symplectic matrix, the two symplectic matrices are related by basis transformation, which means they're similar. They should be similar matrices.
yeah. So you get a new J as,
Yeah,
as a similarity transformation of the old J.
Yeah,
Are,
yeah.
are
yeah,
you trying to
okay.
say something like your new will be the old one, and then you'll have
Yeah.
some like P and
Is J? I guess
I don't know
So
what you
I'm
mean by
thinking
J.
J means Jacobian.
Oh,
sorry.
okay.
Oh no, for me, I mean
Yeah.
that
That is what
matrix.
it is.
What is?
Well,
it's some sense.
that matrix is not. The symplectic thing is not the Jacobian. The thing on
So
the
it'd be
next
like
to it is the
J
Jacobian.
omega J inverse.
Yeah, it'd be like J omega J. If omega is the symplectic
Omega.
structure, it'd be like J omega
So,
J.
so you're
That's what
calling?
was
Are you
going
calling?
on in my head,
Oh,
and so-
omega is that matrix?
Yeah, omega is that matrix.
Okay.
Okay, this is kind of, I digress a little bit, but this you should kind of have in the back of your mind, like, there are other transformations we can do that also are like fine, but they might not look as clean, and so specifically these things don't necessarily get preserved in the original form, and that's kind of what we were talking about. It's kind of like a different representation of that matrix in a different coordinate system. You can kind of think about it like that. So let's get rid of this. Let's go back to what we were talking about. So the question is, okay, so basically we said Lagrangians are equivalent up to, one thing we could do is adding total derivatives, right? So the natural thing to do now is I say I want this to be equal to this now. Oh, by the way, it's traditional, I don't know why, but they sometimes call this K, the new Hamiltonian, the Camiltonian, so I don't know.
The camel?
Yeah, I don't know, so.
That sounds like a bad joke.
Yeah, probably, but I'm just gonna call it K, and this is my original guy, so we're gonna say they're equal to each other. PQ dot minus H equals big PQ minus K, something like that, plus, let's go F dot, so some total time derivative of some function.
Right. Okay. So K is right. Okay. I
This
see.
guy,
Yeah.
yeah.
It's
So I'm
what
just
it's-
distinguishing what they are, right?
Sure.
Okay, now, well, the natural thing to do is to write these as differentials instead. So this is going to be P dq minus H dt equals P dq big Q minus K dt plus F,
DF.
let's see, df. Yeah, sorry. Thank you. Okay, so let's solve for df, right? We want to know kind of what's a natural way of expressing this time derivative thing. If we bring these all over to this side, we're going to end up getting P dq right here, and then we're going to have minus big P dq, big Q, and then we're going to have plus K minus H dt, something like this. And so it's kind of natural to say, let's see where I send my notes at this point. It's kind of natural to presume that f is going to be some function of q, big Q, and t at this point, right? And that's because you notice we have this, those are basically
Oh,
my
those are the
differentials
variables.
there,
Yeah.
right?
Mhm.
And so the reason we want to do that is because now we can explicitly say that the partial of f with respect to q, little q, is going to be p, right? And now we also know that the partial of f with respect to big Q is going to be negative p, or that is the negative of that is equal to p. Big P, wow, you can't really tell the difference between these, but good luck. There's a big P, okay, perfect. And finally, that the partial of f over time is going to be,
Yeah, he's got it.
Oh, it's on the
yeah, it's more standard to write it like that, but I just wrote it backwards. And then the partial of f with respect to t, we're going to get something looking like k plus, oh wait, hold on.
Yeah.
Oh yeah, this is going to be, okay.
Yeah.
Actually, so what people will often write is they'll write what k is equal to, which in this case is h plus the partial of f with respect to time.
Okay.
And I've kind of just rearranged this a little bit, right? If you follow that through. Basically, I said df dt is equal to k minus h, and then we just solve for k, right? Okay, so this is actually really nice because what we figured out is we figured out a way of doing transformations. Because now we have a way of sort of defining these new things in terms of this total derivative that we had, including we know how to modify the Hamiltonian so we get the new Hamiltonian in the correct form. So we have to make sure we include kind of the partial of this function that we created with respect to time. And we also have this structure right here. So this is one version of a canonical transformation, right? And because of what we've done, because we've only added a total derivative, we know that this action functional will still give us the same minimization, and thus it will obey Hamilton's equations of motion. And what's cool is we can now do some tricks to this guy and get some other versions of this as well. They're kind of analogous to a Legendre transformation, but I wouldn't explicitly call them the same thing. I'm going to come over here though to write them out.
Those rules relating big P and little p look a lot like Hamilton's equations.
They do, right. You'll see though that they actually are different for each one of the versions of the canonical transformation, and so it's kind of interesting. Some of them are like the same sign, for example. So they're not all explicitly the same, but it is interesting how they kind of have that same structure. Right, let's go over here now. So let's define a new function phi. We're just going to call this one f plus big P and big Q, right? We're going to note that the differential of phi is going to be the differential of this guy, which is going to be df plus p dq plus q dp, something like that, right? Okay, now we know what this is, right? We actually were working with that over here. So we're going to bring that over. I actually had this written out a different way, so maybe I'll keep it this way. I kind of like this notation better. So partial of f with respect to, let's see, little q, I think is that what that is, dq, plus the partial of f with respect to big Q, dq. If you remember f, I guess I should circle this guy right here. F is in terms of little q, big Q, and t, right? So we need to make sure we get all of those.
And is there a minus sign there?
Sorry, what? Oh,
Is there a minus?
Yeah,
Partial.
that minus cancels with the other minus though.
Oh,
So the minus partial f partial q cancels with the minus
written out
p
any of the
dq.
partials yet.
oh,
Yeah.
oh,
Partials right
oh,
now.
oh, you already did that. Okay.
I guess I could just rewrite it. Would that be? I don't
Oh,
know.
no, that's fine. So we're skipping a step. That's fine. Okay, I can do
No,
that.
no, you're good.
I can do that.
Yeah, no, you're good.
Even I can do that.
So let's look at FDT. Yeah, maybe that was too slow. It's hard to know, sometimes how much to reveal or occlude. Okay, so we got this guy. Now we're gonna plug in what these are. And I was gonna use these. That's the reason I had it written like that, because it's a little bit easier. I guess, like you guys were saying, I could have just plopped that in there.
Yeah.
But so we know that the partial of f with respect to little q is little p. So I can go, and this is gonna be little p dq. This guy right here, we notice is negative p, exactly.
Oh, okay. Oh, okay, yeah.
And then we notice that this
I
guy,
was just jumping the gun. Okay.
with respect to time, is going to be k minus h, right? So, although I don't know, oh yeah, I did put it in there. Yeah, just wanna make sure, k minus h dt. Okay, now what's nice though, and this is kind of the reason we did this whole thing, it might seem we just added something randomly. We did, but it's math magic, so now it's gonna cancel. This guy and this guy are gone. So now notice what our differentials are. We have q, little q, and we have big P, and we have t. So that is to say, phi, it makes sense to think about it as a function in terms of little q, big P, and t. And so by doing this sort of transformation, we've got a new total derivative that we could use that is written differently in terms of these variables instead of these ones, right? And it turns out you can keep doing analogous kind of Legendre transforms like this, and you can end up also, oh, and by the way, if I was to go and explicitly solve this, I would find that P is d phi, oh wow, that's bad phi, let's do that again. D phi, big Q, I have that big Q is d phi d big P, and then I have K equals H plus d phi dt. Anyway, so you can keep doing kind of the same process, the same thing we did over here, right, and get a new transformation system. So you can keep doing this. Oh, by the way, notice now the signs are the same, so that actually changes depending on which ones you choose. It turns out you can choose these total derivative functions to be in terms of a few different options. So I think you can have them in terms of Q and Q. You can have them in terms of Q and big P. I think you can
You
do,
need one small and one big, basically.
I think it's some, yeah, let me think about this. Yeah, I think it's like 2 of each, but anyway, there's like 4 of them. You can look them up. We call these canonical transformations. Anyway, so yeah, that's the first part of my presentation. Any questions on that part? So the answer is we can do transformations to the Hamiltonian, but in order to preserve our symplectic structure properly, we want to do canonical ones because those end up making things look
And
nice.
these define what you mean by canonical.
What I mean by that is in order to
So-
do a transformation, you need to explicitly do something that obeys these things. That we
So back, okay, there. I mean, that's the key to what you're gonna define as
Right,
canonical.
so you have to have some notion of this like function that's kind of a total derivative, and you have to make sure you define your
Okay.
big P's and your big Q's properly such that these hold.
Now, time evolution is considered a canonical transformation too. Have you heard about
I haven't messed
that?
with that one
Okay.
at all, no.
Okay.
I
So
don't
are you
know.
going to Witten now?
Yeah.
Okay, cool.
So yeah, I thought this was